So this is a three-dimensional version of the crypto system I've described in some previous videos. So let me just explain again basically what's happening. I'm treating each row as the binary representation of an integer. Then I'm mapping it to another binary representation with a row permutation on numbers between 0 and 15. So I'll encrypt each row, all 16 of them. Then I'll use another part of the key, the column permutation, to encrypt each column. And finally, I will encrypt what I'm calling the stacks. That's when I'm going to go sort of vertically into the cube. It'll be this one, this one, this one, and this one. That would be the first stack. This one, this one, this one, and this one. That would be the second stack, and so on. So there's 16 rows, 16 columns, and 16 stacks. There's complete symmetry. You need 3 different functions, reversible permutations, that map numbers between 0 and 15 to other numbers between 0 and 15. Any kind of one-to-one function will do. I just select the keys randomly. The key space here, the number of possible keys is 16 factorial cubed, which is a relatively small number. So this really proof of concept version of the system would not be very secure against a serious adversary. However, if you expand the cube, then I think you're going to get a pretty secure system with a massive and exponentially expanding key space. So to decrypt, in general, you want to do everything in reverse order, right? So since I do rows, columns, and stacks, then I want to invert stacks, invert columns, and invert rows. So that's how, if you were just to do one round of encryption, you would do rows, columns, stacks, in this forward way where you apply the permutation. And then you would do stacks, columns, and rows applying the inverse permutations. So it's pretty easy to calculate the inverse if you have sort of the forward or normal permutation. So the spatial relationships are preserved. So you can, if you're encrypting data that already has a discrete 3D structure, that structure is just completely preserved. So this would be a very natural crypto system to apply. And you can also completely view this as just an invertible, 3-dimensional, discrete cellular automaton. So under the hood, we're transforming 4 bits at a time. But in terms of moving from one time step to another, we're moving from the state of 64 bits to a new state of 64 bits. So every bit is a function of all the 63 other bits between time steps. So a change in any of the other bits, the state of any of the other bits, could potentially influence the next state of that particular bit.